Here's another circuit that will oscillate for us, the RLC circuit. You can probably guess what that is. It's got an R, and it's got an L, and it's got a C. A resistor, an inductor, and a capacitor in series. So we use our little fiction here and think about the potential drop around each one and add them up and get 0. So around the capacitor we have a drop of Q over C, negative Q over C. And then, I drew them from a different order from my equations. And then the resistor is, of course, minus IR, is the voltage drop across the resistor. And then the inductor is minus L di dt. Now let's say that's equal to 0. So, more complicated equation. What we want to do is, we want to switch to charge is usually the best thing. So we take our currents to dq dt. And you also, it's usually best when you're dealing with a differential equation to isolate your highest order derivative. So that was going to show up here. We have d2q dt2 there, right? Because I is dq dt, and then a derivative of a derivative is a second derivative. And we want to isolate it, so we want to multiply the whole thing by minus 1 over L. If you multiply that by minus 1 over L, then you'll get plus 1. You'll get just d2q dt2. So if we do that and reorder them a little bit, we get d2q dt2 on that term, plus, and then you would go to your next order derivative. Let's see, that's positive R over L, and then dq dt, and then also positive Q over LC. Where in this case, remember, Q is a function of time. We're trying to figure out how does the charge behave in this circuit. And you multiply the right side by minus 1 over L, and you get 0 on the right side as well. So with the LC circuit, we went through that whole process. We looked at it. We couldn't just solve it by integration. We had to think about it. We guessed a solution. That's what they really do. We guessed, and we plugged our guess in, and we did it in great detail. Now we're going to do it in less detail for this one. We could do the whole thing. And if you knew a lot about complex exponentials, we could do it all in detail. But for this one, just to get us moving along, we're going to guess. And guess is in parentheses here because I'm telling you the right answer because I have done this before. And my guess is Q of t equals A e to the minus bt times the cosine of C. Do I want to use C? Yes, the cosine of CT. So we made sort of a general guess with 3 parameters, where this is some, you can tell, some maximum charge. Right, because this, it's some maximum charge. And BT, this represents the damping. Right, so the circuit has a resistor in it, so maybe you can imagine what's going to happen. It's going to have oscillations, but they might damp. So the damping is in that exponential decaying term, and then the oscillations are going to show up here. So even if I didn't know this was the answer, this is a good constructed solution. Well, it's going to have some amplitude, it's going to be damped, and it's going to oscillate. Seems like a good guess. All right, so let's see what happens with that guess.